We will do some application on Keil and also Proteus today. The first application is given here. Write the 8051 assembly program code that will reverse the LED connected to port 1.0 when the button connected to the LED port 1.7 is pressed. Execute on Proteus model with 8089C51 processor. Set the crystal frequency as 10 MHz. Okay, let's start to examine first the circuit. In here we used 8089C51 because I didn't find our microcontroller model on Proteus. It is the same, approximately same specification with our microcontroller, and we gave before the minimum connection or any microcontroller in the lecture. In here we have Xtol1 and Xtol2. We have a crystal, 2 capacitor and ground. In here we have a reset circuit, EA pin, external access pin, as you see. If it is 1 or logic 1, it is mean that we will use internal data memory. We have to set up also ground and supply voltage, but they are hidden pins on this microcontroller. If you click 2 times, you can see hidden pins as ground and VCC. Okay. Okay, what is the application for today? Yes. We need a reversed LED connected to port 1.0 when the button connected to port 1.7 is pressed. Okay, so we need a machine code for this model. Okay, to get the machine code we need a program code. Okay, so we have to pull the port 1.7. How? Jump if bit port 1.7 is 1, wait here, but if it is pressed, we will continue from line 4, and here we need a CPL complement, it's mean port 1.0, and then sjump X. That's all. This is the needed program for this question. So we can compile this program, no error, no warning, and hex file is created in this path. So we need to load this machine code to here. How? Program file path, as you see here, we have to select it. I don't know what is the path for your computer, but I know my machine code file in this folder path, and then it's okay. Let's try this program now. Start the program. The LED is turned on, as you see. Why? Because we know all ports are FF at the starting point. If you don't clear the related LED or related ports. Okay. When I press the button, as you see here, LED is complemented. Okay, let is complemented. When I pressed one more time, turn on and turn off again, turn on, turn off, turn on, turned off. As you see here, it is working. Okay, maybe we can try the reset circuit. If I click this button, LED should be turned on again because it is the starting point. But it is needed for at least 2 machine cycle according to the RC time constant. Okay, it is working. This is the first application for this lecture. Let's continue. If you don't have any question, it seems that the system given in experiment 1.1 sometimes makes more than one inversion when the button is pressed and therefore doesn't work stable. How? We can try it. I'll click one time, but as you see here, turn off and turn on again. Turn off and turn on again. It is not working as stable, right? When I pressed, it will be turn on, turn off, but we cannot consider it because it is so speed, so faster. Okay. Then observe that the LED is inverted at a visible frequency by creating a delay after inversion with the nested loop structure. So we need a delay after the inverted or the LED. How? With the nested loop structure. Okay, we will use nested loop structure. Maybe I can give you the time needed. 250 times 250 times 5. We need 3 nested loop structure. It will be as like that. Now please do it and give me the program codes, related program codes. We have a response as like that. Let's examine these program codes. Okay, just we have an error in here. It should be not x2, it should be x1. Okay, for the nested subprogram. Until this program line, we have 250 times 250 times 5 nested loop. Okay, first of all, we will wait for the pressing of the button and then we will convert it, and we have a delay in here with the nested loop structure. Now we can try the compiling of this program. Yes, we have no error and no warning. And then we can continue from the Proteus model. To do this, we have to select again and again if you do any changing on your program codes. Okay, then we can start. Yes, as you see here, it is more stable now. When I press the button, it is inverted. LED is inverted. Okay, if we pressed and not released, we can see the LED is turned on and turned off. How? In this program, we converted the related LED and we have a delay with the nested loop, and we will go to the sjump start again, and if you don't release the button, this condition is not satisfied and program will continue with line 7. It means LED is inverted again. Okay. It seems that the system given in experiment 1.1 sometimes makes more than one inversion when the button is pressed and therefore does not work stable. Yes, we can see it before. Make the necessary changes in the program code so that inverting can be made only once per button is pressed. In this application, we don't want to write any delay, or you can write no problem, but we want if you pushed one time, so LED is only changed one time. Okay, how can we do it? First of all, I will explain this program codes. In here, we check the button condition. It is 0 or not. If it is 0, the program will stay in this line. But we know this, all pins are logic 1 at the starting. So program will continue with this with this line. And in this line, if it is 1, we'll go to the XX2 again. XX2. Why? Because in here, if we pressed, the program will confused. So if we use here, I think XX1 for example, and if it is XX1, there is no problem, I think. Let's try it. Yes, we'll load the program codes now and try it. There is no problem. Maybe we can try another way. XX2. Yes, no problem. I think sometimes it should be not working as through. As you see here, I pushed one time, but condition doesn't change. Okay, it is not working as stable. For the clarity, we can modify the program as like that. First of all, we will check the button condition. If it is 1, program will stay here, and then converted the related let, and then it will continue, it will wait in this line. If we don't release the button, program will stay here. If we released, program will go to the XX2. Okay, it is more clear, I think, for you. Let's try it. It is so easy for you. Perform the operation required for the system given in experiment 1.1 when the button is pressed and released. So we can do this application together. This is pressed condition, and this is released condition. That's all. We can try it. Syntax, yes. Let's try it now. Yes, I push the button, but let is not converted because I have not released yet. If I release the button, let will be converted. Okay. Okay. What is the last application? Repeat the desired operation with experiment 1.4 for the case that the LED is connected to the port 0.0 and the button is connected to the port 0.7. Okay. Now we will change port 1.0 as port 0.0 and port 1.7 as port 0.7. What is the difference of the two applications? What do you think? Okay, as you know, we need a pull-up resistor if we use port 0. Okay, if we use port 0, for the communication with the physical world and microcontroller, we need to connect pull-up resistor. There is only difference, we can say as like that. Where is the project file? I'll show you now. Yes, here we have a pull-up resistor, port 0.0 and port 0.7. Okay. For the LED, we have a voltage divider here, 100 and 100 ohms, and for the button we used 10 kilo ohm pull-up resistor. You can increase the resistor value on this resistor value, but current will be decreased, so you cannot see the changing on this LED. Okay, what is the needed program codes in here? Let's try it. Compile it and then we can try. Okay, as you see here, that is turned on. If I click one time and release, turn off. If we didn't use pull-up resistor, what will be happen? Let's try it. We don't have a pull-up resistor now. As you see here, the button or pin condition is not known, and LED is not turned on. Okay.